you can consider what I have told you up to now to be a very brief introduction to the world of fluid mechanics. So now let's get down to real work. Usually we say a discipline of mechanics is comprised of two parts, statics and dynamics. In statics, the thing we're studying is not moving, it's not in motion, but in dynamics, it is. So I think it's simpler for us to first study the easier one, which is statics. So our first topic will be fluid statics or hydrostatics. In this background, if we have a cup of water, let's say, the water here is not moving. Okay, so if we want to study the fluid, remember what I said to you, the research subject of fluid mechanics usually is not the fluid molecules themselves, rather fluid particles. So let me give you an example how that works. Here we take out a small sample of the fluid, and we can call that sample a fluid particle. It's easier for us to just investigate into a small cube rather than a ball or something, by the way. Okay, so this direction, horizontal to the right, let's call it the x direction. And this direction, horizontal to the back. And here in the picture, it's perpendicular to the paper, this direction. And z direction is vertical up. Let's also call this point, the location of this point, or the coordinate of this point, to be x, y, z. Okay, so remember I told you a fluid particle is very small. What is its volume? It only has a differential volume. So we can say the volume of this small cube will be dV. And obviously, each dimension of our little cube will also be differential. So this dimension, let's call it dx, and this dimension dy, this dimension dz. So can you tell me the coordinate or the location of this point? That will be x plus dx, y, z. And the location of this point, x plus dx, y plus dy, z plus dz. Okay, so our fluid is not moving. The bulk fluid is not moving. So obviously our little cube is not moving either. So what's another way to put that? What's another way of stating something is not in motion? Newton told us that. It's in what kind of state? It's in equilibrium, right? Also, you can say it's in balance, or the net force acting on this thing will be 0. So if we write sigma f, the whole net force acting on this cube equals to 0, how many equations do we have? Actually, we have 3. Because force is a vector, we can divide the equation into 3 components in x, y, and z direction respectively, right? So let's consider them one by one. Let's first say the x direction. In the x direction, all the forces acting on the x direction, that is the net force of the x direction, will equal to 0. So what are the forces acting on the cube in the x direction? Or what are the x component of the forces acting on this cube? Well, in fluid mechanics, usually we can divide forces into 2 categories. One is called body force. Body force obviously is something that is acting on the whole body, on the whole particle, right? So do we have that kind of force? Do we have body force acting on this cube? Actually, we do. We have the gravity, right? But do we have a body force or a component of body force in the x direction? That we do not have, because the x direction is a horizontal direction, and the gravity only acts on the vertical direction. So in the x direction, we do not have the effect of gravity, and we do not have any other body force. So in the x direction, we do not have the effect of body force. But later, when analyzing the z direction, obviously we need to introduce the effect of gravity. So bear that in mind. Okay, so another kind of force, another category of force is called the surface force. Surface force, as the name states, is a kind of force that acts on the faces, on the sides of our cube. So do we have that kind of force acting on the x direction? Here we do have. That is the force caused by pressure. You see, if we have a certain depth of water, then a pressure will be induced, right? So here we'll have a pressure. And the pressure itself is a scalar. So it do not have a specific direction. Say we have a point here, and pressure acting at that point will be acting on all directions. But if we want to investigate into a force caused by pressure, then we need to introduce a surface. And the force caused by pressure is acting, its direction is perpendicular to the surface. So let's say if we have a surface here and we want to know the pressure, the force resulting from pressure acting on this surface, then it's in what direction? It's perpendicular to our surface, right? So it's this pressure. So it's the force caused by these pressures. So now we want to have a force. We want to have a force caused by pressure acting on the x direction. So what kind of surface are we looking for? A surface that is perpendicular to the x direction, right? In that case, the force caused by pressure will be acting in the x direction. So what are the surfaces that are perpendicular to the x direction? The left side and the right side, of course. So we need to add all the forces caused by pressure on the left side and on the right side. So maybe let's first consider the left side. As I have said, this volume is only a differential volume, so it's very small. And let's say on a certain surface, on a certain side, the left side, the property here and the property here, or the property in the middle of this side will all be very similar, right? So we know that to be the most accurate, we need to how do we get the force resulting from pressure acting on the left side? We need to integrate the pressure over this area. But actually here we do not. We can use an approximation by using an averaging principle. As I have said, the property here or the property here, that is the property over the face, are all very similar. So maybe we can just choose a representative of the surface and multiply by the area of this face, and then we get the total force resulting from pressure acting on this face, right? So we might as well choose a representative from here, right? this XYZ point is on the left side. So we can choose that to be the representative. So we can say the pressure acting on the left side, or to be more accurate, the force resulting from pressure acting on the left side will be what? Will be the representative pressure. The pressure at XYZ times the whole area, which is dy dz. Is this in what direction does this point? In the positive x direction, right? The pressure acting on this surface will be like this, so it's in the positive x direction. So another force we need to introduce in this equation will be the force resulting from pressure acting on the right side. Well, by the way, the name pressure itself in English, sometimes it can refer to the intensity of a pressure force, right? That is the pressure force acting on unit area. But sometimes it can just refer to the pressure force itself. So it's a little confusing. But in Chinese, the pressure itself and the force caused by pressure are two different terms. So bear that in mind. Okay, so on the right side, for the same reasoning, we can also choose a representative pressure and then times the whole area, right, to get the total force acting on the right side resulting from pressure. So we can just choose an arbitrary point on this side to be our representative. Let's say this point. This point will be x plus dx yz. So here we have a pressure called the pressure at x plus dx yz. And we need to multiply by the total area of the right side, which will be dy dz. And the force are like this, the pressure are like this. So the total force will be in what direction? In the negative x direction. So here we need to put a minus sign. And this thing is just all the forces acting on the x direction. So this will equal to 0. Here we do a small trick. Let's divide both sides by dv. dv equals what? dv, this is a cube, right? So the volume will be dx dy dz. So now let's divide both sides by dx dy dz. What do we have? P minus px, let's say. The y and z here are not changed, right? So the two pressure only have a difference in the x direction. They do not have a difference in both y and z direction. So let's just call it px, because in a sense we can say the pressure here do not change with y and z direction, right? Do not change with y and z direction, or y and z direction do not affect our pressure. So px minus px plus dx here. We divided both sides by dx, dy, dz. So dy, dz are cancelled, and we are left a dx on the denominator. So this is what we have. This is equal to 0. So as dx goes to 0, what is this thing? Well, this is the negative of the pressure change with respect to x direction, right? As dx goes to 0. So actually, if we let dx tend to 0, we result in a differential equation resulting from this equation, which is partial p partial x equals to 0. So this is what we have.